All right. Good afternoon, everyone. So I had a few requests come in for particular problems. So I thought I would go over those and just kind of do a general review of the test material, or the material over which you will be tested, excuse me. So without further ado, let's just dive on into it. So one of the questions I was asked in particular was, find the integral 4x squared minus 3x plus 2 over 4x squared minus 4x plus 3 dx. Now, I'm going to say this right now, but my notation is going to be a little sloppy here because this problem is so long and I have such a small area on which to write. So I'm going to have to do this in pieces, and it's going to be a little, it might be a little hard to follow, but just go ahead and rewind the video if you're having trouble following. So we're going to begin by dividing. Using polynomial long division. So 4x squared minus 4x plus 3 into 4x squared minus 3x plus 2. So we ask ourselves, what do we need to multiply by 4x squared to get 4x squared? Well, it's just a 1. So we go ahead and multiply. We get 4x squared minus 4x plus 3, and then subtract using our parentheses. 4x squared minus 4x squared is 0, so that cancels. Minus 3x minus minus is plus 4x, so that's positive x, and then 2 minus 3 is minus 1. Now this has a lower degree than this, so we're going to go ahead and stop there. We have our remainder. Okay. So I'll put a star here for easy reference. So star is equal to 1, because we divided that out, plus x minus 1 over 4x squared minus 4x plus 3. Sorry about that. Dx. Okay. So again, I'm going to have to do this in pieces. So I'll go ahead and erase this and copy this up here. So that's integral 1 plus x minus 1 over 4x squared minus 4x plus 3 dx. Okay. So I'm going to label these a little bit. So we can split the integral, and we have realistically 2 integrals here. So A is going to be really easy to compute. We know how to do those. Those are easy. B is going to require a little bit more work. So you may be thinking to yourself, okay, well, maybe this, maybe B is partial fraction decomposition, right? And we can see whether or not that's necessary by seeing if the denominator has any roots or zeros. And we can determine that by using b squared minus 4ac, because if this value is negative, that implies that there's no roots. So if we have b is minus 4, so that's 16 minus 4 times 3. Well, that's bigger than 16, so this is certainly less than 0. So there's no roots. So partial fraction decomposition isn't the path that we want to go down with this particular one. So one option we have is we can complete the square. Okay, so I'm going to factor out a 4. And I'm going to complete the square inside these parentheses. Okay, and you'll recall, to complete the square, we're going to add b over 2 squared. Okay, so b is -1 in this case. So this is x squared minus x. And then I'm going to add negative 1 over 2 squared, which is 1/4. And then I'm going to subtract 1/4. So I didn't change the value of what was inside the parentheses at all. I just added a very fancy 0. Well, now this factors. So this becomes 4 times x minus 1/2 quantity squared, and then minus 1/4 plus 3/4 is plus 1/2. And then we can go ahead and shove that 4 through. So that's 4x minus 1/2 quantity squared plus 2. And if we write this in a very fancy way, we can go ahead and push that through as well. So that's 2x minus 1 quantity squared plus 2. Okay. So we've completed the square, so we can go ahead and rewrite that denominator as this instead. So I'm going to have to erase here. So this is 1 plus x minus 1 over 2x minus 1 squared plus 2 dx. Okay. Now it gets a little tricky, but I don't think it's anything we can't handle. So again, when we're just working on b right now. So this is a u sub. We let u we let u equal to 2x minus 1. Then du is 2 dx. So dx is du over 2. Now, the real trick here is realizing that we can use this to solve for x and substitute that in. And that's what we're going to have to do. So u plus 1 over 2 is equal to x. So that's, we'll go ahead and rewrite this as u over 2 plus 1/2 is equal to x. Let's see if I did that correctly. U plus 1 over 2. Yeah, okay. So now we can make our substitution. So I'm going to say b is the integral x minus 1 over 2x minus 1 squared plus 2 dx. After making our substitutions, so we can go ahead and substitute this in for x, and the 1 in the, or the negative 1 and the 1/2 are going to make negative 1/2. So this is u over 2 minus 1/2. And when we substitute the dx, I'll go ahead and bring that 1/2 out front. So we have du over u squared plus 2. Okay. So we can go ahead and factor another 1/2 out of the numerator and get 1/4 u minus 1 over u squared plus 2 du. And now we can split the integral. So b kind of splits into 2 pieces. So now we have integral u over u squared plus 2 du. And I'm going to label this Roman numeral, was it 1 or I or whatever. And then we have 1/4 minus 1 over u squared plus 2. Okay, so this is a u sub problem. Like I said, it's definitely messy. So we'll let omega equal u squared plus 2. And then d omega is 2u du. And I'll just go ahead and move that 2 over. Equals u du. Okay. So when we go ahead and make our substitution, we have that the integral I is 1/8. In fact, accounting for this 2 here. Integral d omega up top over omega, which is 1/8 log of the absolute value of omega. Okay, and then we need to unwind that and put it back in terms of u. Okay, so in terms of u, this is 1/8 log absolute value u squared plus 2. And then we started with x's, so we want to finish with x's. So now the last thing we need to do is unwind this back to x's. So if you'll recall, our u was 2x minus 1. I may have a sign error here. Sorry. No, it should be 2x minus 1. Okay. So 1/8 log absolute value 2x minus 1 squared plus 2. So the last thing to realize here is that we can actually drop the absolute value, because what's in the absolute value is going to be positive no matter what. We're squaring something and then adding a positive number to it. That's always positive. So in fact, we can actually drop off the absolute value, but we need to provide justification why we can do this. So that's 2x minus 1 squared plus 2. Okay? So I'm going to put this up here. The value of this integral I is 1/8 log 2x minus 1 squared plus 2. And then we've taken care of that piece right there. Okay? So, yeah, I need to erase. And then now we can call this II. So we have II is negative integral negative 1/4 integral 1 over u squared plus 2 du. I forgot my du over here. So we can factor a 2. Well, we can factor a root 2 squared. We're going to do a little fancy trick here out of the denominator and end up with 1 over 4 times let's see, how do I want to phrase this? This is the form of an arctangent. So that's what we're looking to do here. So we'll go ahead and write this as 1 over 4, and then I'm sorry, I lost my place here. This problem is pretty hairy. It took me almost 3 pages to make sure I had this right. So bear with me for a second here. Okay, minus 1 over 4 integral 1 over So we'll do u over root 2 quantity squared. And then let's make sure this gets us to where we need to go. So that'd be u squared over 2, 1. We can change that to an 8. I think that'll work. All right, where were we at? Okay. So now, I don't want to do another u substitution, but that would be the clearest way to finish this. But if you take my word, once you factor out the constants and everything, you should end up with, if you were to go through and do the u substitution, you'll pick up, and like you can rationalize, and you should end up with a cancellation. So you end up with negative 1 over 4 root 2 tan inverse of 2x, sorry, of u over square root of 2 and plus our constant. And then when we switch back to x's, we had 2x minus 1 over root 2 plus c. Okay, so I is minus 1 over 4 root 2 tan inverse. I trust you guys to go ahead and finish that u substitution. It's just I'm running out of room here, and I don't think you all need to see that again. I know you can do that. So okay. So we had that piece, we had that piece. We're ready to put this all together. Okay, so I'm going to erase some more over here. All right, so we can go ahead and integrate a. Well, what's the integral of 1 dx? That's just x, so that was easy. And then, like I said, b splits into 2 pieces. Okay, so the first piece is plus 1/8 log of 2x minus 1 squared plus 2. Yeah, 2x minus 1 squared plus 2. And then minus 1 over 4 root 2 tan inverse 2x minus 1 over square root of 2 plus c. This problem is definitely a bit of a beast. So all our stuff is back in terms of x's. We've cleared out our substitutions. We added all the pieces that we had together. So we're done here. Definitely not the most pleasant problem I've ever worked on. But okay. Wanted to cover a trig sub problem and kind of let you all know how I envision these going. So, you know, if you have any questions, we can be on a similar page of how these things should go. So we want to find the integral of 1 over x squared times x squared plus 4. Now this fits the form of a tangent substitution. It's an a squared plus x squared, right? So we can say let x equals to 2 tangent of theta, and we're picking the branch of tangent between minus pi over 2 and pi over 2, or where theta is from minus pi over 2 to pi over 2, okay? So then our dx becomes 2 secant squared theta d theta. Okay. So our integral then is 1 over x is 2 tan theta, so x squared is 4 tangent squared theta. And then I'm going to come off to the side here, and we'll have to recall these Pythagorean identities to really notice what's going on here. But we have x squared plus 4, so that's 4 tangent squared theta plus 4. If you'll recall from our Pythagorean identities, this is equal to 4 secant squared theta. So when we go to substitute into here, we can just replace it with this, which is 4 secant squared theta. Okay. I need a little bit more room here because our dx then becomes 2 secant squared theta d theta. Okay. So we can go ahead and take the square root here. So this is integral, and I'll cancel the 2 and the 4 here. So this is secant squared theta d theta over 2 tangent squared theta times 2, and then this is the absolute value of secant theta. Because if another way to define the absolute value of x is to first square it and then take the square root of x squared. So we need to justify, we want to get rid of the absolute value. We don't know how to integrate something with an absolute value, right? So we need to justify why we can do that. Well, on this branch between negative pi over 2 and pi over 2, the values of cosine are positive. And if the values of cosine are positive, then the values of secant are positive. So with that justification, we can go ahead and drop these absolute values here. So that was what? 2 secant theta, right? Then we can cancel. So we have 1 over 4 d theta over tangent squared. Sorry, we're missing a secant theta. Secant theta d theta over tangent squared theta. All right. So I prefer to work with sines and cosines. So I'm going to go ahead and write this as integral 1 over cosine theta over sine squared theta over cosine squared theta d theta. And if we flip, multiply, and cancel, we end up with 1/4 integral of cosine theta over sine squared theta d theta. Okay. Now it's a u subproblem. So we let u equals to sine theta, du is cosine theta d theta. So this is 1 over 4 integral 1 over u squared du, not d theta. Okay, and then that's 1 over 4 times minus 1 over u plus a constant. And then we switch back into the realm of thetas. So that's minus 1 over 4 times 1 over, and our u was sine theta, plus c. Now, we want to switch back into x's because we started with x's, we want to finish with x's. We're going to need to draw a triangle, and I'm going to use this space up here. So our original substitution said that x was 2 tan theta, which tells us that tangent of theta is x over 2. And we know that tangent is opposite over adjacent. So we can go ahead and draw a triangle and opposite over adjacent. So that's x and 2. And the hypotenuse is x squared plus 4, just using the Pythagorean theorem. Okay? So if we want sine of theta in terms of x, sine of theta is opposite over hypotenuse. So that's x over x squared, sorry, square root of x squared plus 4. So now we're ready to put everything in terms of x's. So this is minus 1 over 4. Sine of theta was x over square root x squared plus 4. And when we simplify this, this is minus square root x squared plus 4 over 4x, and I forgot my plus c, plus c. So we're done. 2 substitutions is not the easiest thing in the world to keep track of. I'll be the first one to admit that. Okay. Next, we have an improper integral. 0 to infinity. This one was also by request, and it's also pretty gnarly. We have arctan dx over 1 plus x squared quantity squared. So the hint was let u equals to tan inverse of x and integrate by parts, which means that dv is equal to x over 1 plus x squared squared dx. So right off the bat, we have to figure out what's v. Because if we wanted to set up an integration by parts, we're going to need a v, right? So to find that, we're going to need to integrate this. All right, let's get to it then. So we want the integral of x over 1 plus x squared quantity squared dx. Well, let's let omega equal to 1 plus x squared. Then d omega is 2x dx. So d omega over 2 is x dx. And then we can go ahead and make our substitution. So this is 1/2 d omega over omega squared. Which we just computed an integral like this, so I'm not gonna go through the whole thing, but this is 1/2 minus 1 over omega plus c is negative 1/2 or 2 omega. Well, we can go ahead and switch back now, so we don't need omegas. 2 times 1 plus x squared plus c. And we're gonna for the purposes of integration by parts, to find the v, we're not going to mess with the plus c. So we'll call this our v. Okay, so I'm going to erase a little bit here because this is also a very long problem. So we have u, we have dv. Our v is minus 1 over 2 1 plus x squared. And du is 1 over 1 plus x squared dx. Okay. All right. So now, so the way I prefer to work with improper integrals that are particularly nasty like this is I like to find the antiderivative first, and then we'll add the extra layer of complexity in taking the limits on top of that. So that's what this whole exercise is for. It's just finding the general antiderivative of this, and then we don't have to do all of this calculation with limits involved. So if I were writing this down like on a test, for example, I would specify that, okay, I'm going to find the antiderivative first, and then we'll deal with the limits. I would try and put this as much on the side as possible, but I just don't have that room. So, okay, where was I? Right, okay, so now we need integral of v times du, which we can go ahead and write as negative 1/2 1 over 1 plus x squared squared. Okay. And that's dx. Okay, well, another trig subproblem. So we have x is equal to tangent of u, which tells us that dx is secant squared of u du. So we go ahead and make our substitution. That's minus 1/2 integral secant squared u du over we have, if we substitute tan in directly, we'll get 1 plus tangent squared of u, which with our Pythagorean identities just ends up being secant squared of u. So the denominator becomes secant to the 4th of u. Just trying to save a little bit of time here. So we can go ahead and cancel. We get minus 1/2 integral 1 over secant squared u du is minus 1/2 integral cosine squared of u du. And we know how to integrate that by using a power reduction identity. That's negative 1/2 times integral of 1/2 plus cosine 2u over 2 du is minus 1/2 times 1/2, or sorry, I'm going to go ahead and put a bracket out here just to make things a little bit easier. So that'll be 1/2 u plus 1/2, and then that's times 1/2 sine of 2u. And again, since this is just for integration, since this is, we're just finding the antiderivative, and this is a definite integral, we're not going to mess with the plus c's. This is, again, just to find the antiderivative. There's a little bit of nuance there. So if you're wondering where my plus c's are going, that's why. Okay, so now we need to put everything back in terms of x's. So we can use, where were we? U over here, we can use this to say, well, u is inverse tangent of x. Okay, so we'll go ahead and feed that in. We have minus 1/2 tangent inverse of x plus 1/4 sine of 2 tangent inverse of x bracket. Okay. Okay, so now we can do some erasing, and we're ready to piece this together. So I'll leave this for now. So recall that the integral of u dv is uv minus integral v du, right? Well, we have this and we have this. So the antiderivative of x tan inverse of x dx over 1 plus x squared quantity squared is equal to our u times our v is minus tan inverse of x over 2 1 plus x squared. Let me just make sure I agree with my notes here. This problem's pretty easy to get lost in the weeds. There's a lot going on. Okay, yeah, that agrees. All right. And then minus integral. So we figured out what that integral is, and it's this quantity here. So the minus and the minus are going to cancel out. And we actually have plus 1/2 tangent inverse x plus 1/4 sine 2 tangent inverse of x bracket. Okay. Now we're ready to take some limits, okay? So I'm gonna erase this little bit up here. Like I said, just trying to keep this as clean as possible. So I'm gonna copy up here because I'm gonna have to take this limit in pieces as well. And that's 1/2 tangent inverse of x plus 1/4 sine 2 tan inverse of x. Okay. All right, to set up an improper integral, we need to say that the integral from 0 to infinity x arctan of x dx over 1 plus x squared is the same thing as limit as b approaches infinity of the integral from 0 to b of the same integrand x tan inverse of x over 1 plus x squared dx, right? So we have the antiderivative, so we need to go ahead and evaluate that at the top and bottom piece. So I simply don't have the room, so I'm just going to address this part first. If we think about what happens when we evaluate the lower bound, in the denominator we have 2 times 1 plus 0, so the denominator is non-zero. But the numerator, inverse tangent of 0 is. So when we evaluate the lower bound, we don't actually get anything. It's 0. So we have limit as b goes to infinity of minus tan inverse of b over 2 1 plus b squared. Okay, and it's a property of limits that this is the same as limit b goes to infinity minus tan inverse of b over, limit b goes to infinity 2 1 plus b squared. All right, so the numerator is finite. Inverse tangent is bounded above by pi over 2, right? So this is pi over 2, but our denominator is unbounded. So this entire thing goes to 0. Okay, so that's generally what we like to see when doing these improper integrals. Like the more things that go to 0, generally the easier our life is. So the part, if you'll recall, the uv minus integral v du, this part actually contributed nothing to the integral because when we took the limit, it all went to 0. Okay, so now we need to take the limit of the other piece. So we're not getting infinity, which is good. That means that we have a pretty lot, or we haven't gotten infinity yet, which means that there's a pretty good chance of this converging. So now we need to look at limit as b goes to infinity. So I'm going to go ahead and distribute that 1/2 through. So this is 1/4 tan inverse of the upper bound, which is b, plus 1/8 sine tan inverse of, 2 tan inverse of b minus, and then the lower bound is 1/4 tan inverse of 0, but again, that's 0. minus 1/8 sine 2 tan inverse of 0. Tan inverse of 0 is 0. And then that goes into sine, and sine of 0 is 0. So the lower bound, again, gives us nothing. I suppose I should have my parentheses here. All right, so the lower bound gives us nothing again. So really all we're concerned with is this piece. Okay, so the limit of a sum is the sum of the limits. So when we take the limit of the first term, that becomes 1/4 lim b goes to infinity tan inverse of b. And I'm going to use a slick trick here, but sorry, plus 1/8 lim b goes to infinity sine of 2 tangent inverse of b. Okay, now the trick here is that since sine is a continuous function, we can exchange it and the limit. So this first piece here is pi over 2. So 1/4 times pi over 2 is pi over 8. And then we have plus 1/8 sine of the limit as b goes to infinity of 2 tangent inverse of b. Well, that's pi over, if let's pull the 2 out, it'll be easier to see that way. But this value here is just pi over 2. And then we multiply it by that 2 and we get pi, and then sine of pi is 0. So this whole thing is 0. All we're left with is pi over 8, which is finite. Therefore, the improper integral converges, and its value is pi over 8, and we're done. These problems are pretty hairy. So I just wanted to review a couple more things. Euler's method. So here's a problem. We want to estimate the value at t equals 0.5 seconds with step size 0.1. We have di dt is 15 minus 3i, I of 0 equals 0. So our initial value, or our first value, I1, is our initial value, the y, 0, plus our step size, 0.1, times our differential equation, 15 minus 3, evaluated at I is 0, or our x naught. So this is our y naught, this is our x naught. 3 times 0. And when we turn the handle, it's 1.5. So now we store this in short-term memory here, and then we say, okay, well, I2 is 1.5 plus 0.1 times 15 minus, and now we have a new a new value to evaluate here. So this, in this problem, you can think of I as being y. So I misspoke earlier. This should be this here, this 0, not the x 0. So apologies. So the value that goes in here is 1.5, and when we turn the handle, that's 2.55. I3 is 2.55 plus step size 0.1, 15 minus, and again, since this doesn't concern x's, we're not plugging in any x's, so that would be 3 times 2.55. Turn the handle, we get 3.285 I4. Excuse me. I4 is 3.285 plus step size, 15 minus 3 times 3.285 285, and we get 3.7995, and then lastly, I5 is 3.7995 plus step size 0.1 times 15 minus 3 times 3.7995. And when we turn the handle, it's 4.15965. So Euler's method, not particularly deep, just, it's more of a plug and chug. Just know the formula inside and out. And same thing with your approximate integration. There's not a lot of thought involved. You just need to make sure that you have your delta x value correct and your problem setup is correct for approximate integration. And then the rest is, honestly should be left to a calculator. It's good to know how these things work, but I'm not sure how much you're going to get out of doing a bunch of arithmetic by hand. All right. Lastly, separable equations. So here's an example. dy dx is x squared over y squared with the initial condition of y of 0 is equal to 2. So y squared dy is x squared dx just by multiplying both sides by y squared and dx respectively. And then we can integrate and we get y cubed over 3 is x cubed over 3 plus c. And technically we get a constant from the left-hand side and a constant from the right-hand side, but we can just subtract it over and make one constant, right? So that doesn't matter. And then we go ahead and solve for y. So y cubed is x cubed plus 3c, and y is cube root x cubed plus 3c. Okay, now we apply the initial condition. So y of 0 equals 2. So we have that the cube root of 0 plus 3c. So 3c is equal to 2, which tells us that 3c is equal to 8 by cubing both sides, or that c is equal to 8 over 3. Okay, and now we're ready to give the general form of the solution just by substituting back in that c. So y is a function of x is the cube root of x cubed plus 3c, so the 3's cancel, so x cubed plus 8. We're done. So separable equations, not too difficult. Get all of the things with y on one side, all of the things with x on one side, integrate, and then solve for y. Apply initial condition. They're pretty straightforward. And the last thing I wanted to touch on was I just wanted to remind you all about the trick. The b squared minus 4ac is less than 0. For quadratics, if this is true, then they don't have any roots. And for quadratics, if there's no roots, then it's what we call irreducible. So when you're thinking about doing a partial fraction decomposition, you think that maybe it's not factorable, right? That's a quick way to tell if something's not factorable, is if this condition is true. So remember that repeated linear factors and quadratic factors in the denominator have special forms. So be sure to memorize when and how to use those. That's pretty important. Those partial fractions can get pretty hairy as well. So that's all I wanted to cover. I think that does it. So I'm gonna say goodbye for now, and good luck on the exam.